You okay, Steve? So our next speaker today is Jesper Jacobsen, and he's going to tell us about representations and partition function zeros of the Potts model with and without boundaries.
Thank you. It's a real pleasure to be here. So thanks to everybody for organizing this event. So my talk is going to link up with a lot of what Professor Biggs just talked about, and also to the talks by Zhang and by Shrug. And hopefully it will also introduce something which is new to you. So I should say that the bulk part of the work which is presented here is done with Hubert Saller and our joint thesis student Jérôme Dubail. And also I'll just find the occasion of touching on some joint work that I have done with Alan Sokol, mainly to remind him that we have to write it up quite soon. So here we go. So I'm going to tell you about how partition function zeros for the Potts model and for the chromatic polynomial in particular is linked up with various representations that you can have of the Potts model. So I'm going in the first section to present various kinds of disguises for the Potts model. And in the second part, I'm going to make that a little bit more explicit by showing how that carries over to the transfer matrix structure. So something that that Biggs just discussed. There's going to be a very short third section, which could have been expanded out to fill the entire talk, but it comes more from the physics side, so I'm trying to keep that in the background and just stating the few results that I have to use. And then the grand conclusion is going to be in the fourth part. So let me not waste too much time on the Fortuyn-Castelline representation that you have seen so many times. So the partition function of the Potts model can be written in this way. Q is the number of states. So as a sum over edge subsets, Q to the number of connected components in the induced graph, and then there's this product over the variables V. So that we have seen a lot of times. Let me actually go a little bit in the direction of what Alan Sokol has said so often. He wants the multivariate Tutt polynomial, in which V is in some sense made a local variable. So what I'm going to discuss here goes in the direction of making also Q a local variable. So if you take the utter consequence of what I'm going to do, you should have a different Q for each subset of vertices in your graph. Okay, but apart from that, I'm going to present to you a new concept, which eventually will lead to what I'll call the boundary chromatic polynomial. So the idea is that I'm going to consider here only planar graphs, which are always embedded in an annulus. So you can imagine them to be strip graphs, recursive families of strip graphs where I have periodic boundary conditions identifying top and bottom. And so I have some graph in here. Might be a portion of the square lattice, it might be something more complicated. But the main idea is that some of the vertices reside on the left boundary and some vertices reside on the right boundary. So I'm going to distinguish those, and I'm going to say that the number of colors that you have inside your system in bulk vertices is still going to be Q, but there's a different number of colors on the left and the right boundaries, which I'll call QL, Q for Q left, and QR, Q right. So just for starters, you can imagine that everything is integers. So you can imagine that Q is larger than Q left and Q is larger than Q right, so that you have a subset of your colors living on the left and the right. So left and right spins are constrained. And moreover, if you take two different subsets, they may have a non-trivial intersection. So there's something called QB, which is be for both, which is the common number of colors between left and right. So if I do that, then using exactly the same construction, my partition function is going to look like this. Let C be any number of clusters, including clusters which touch the left or right rim, and let CL be clusters which touch the left rim but never the right, CR, those who touch the right rim but never the left, and C both, those which touch both left and right.
And this actually has an interpretation in terms of colorings also, right?
Yes.
You can say, for example, if Q is a large integer, and you say both sites can be colored 1 through Q,
right,
but sites on the left and right boundaries have certain numbers.
There are certain forbidden colors, and the forbidden colors don't need to be the same on the left and the right.
Exactly.
So this QB is still a non-trivial thing. So imagine that I have in the interior I can have red, blue, green, and white. Here I can have red, blue, green, and here I can have red, blue, white. So then Q would be 4, Q left, Q right would be 3, and Q both would be 2. Okay.
So
you can cite no restriction.
Right.
Right.
But then, this polynomial is restricted to not only Q integer, but Q1, Q left, Q right, and QB are all Q minus some fixed numbers.
Yes.
Then that restriction would have a coloring interpretation.
Right.
It's not quite a list coloring polynomial as Carsten Thomason wanted, but it's some very special case of one.
Right. And of course you can try to make things more general. So here there are 2 natural rims on my system. So I want to think in terms of those, but you might want to make things more general. Okay, so I can make this random cluster expansion. So you see the fact that I divide by Q here is just saying that some of the clusters are clusters touching only left. So I divide by a Q for each of those, and I multiply by Q left and, instead of that. And now once I have got this, I don't need any of these guys to be integers, and I don't need any of them to be smaller than the others. They are just arbitrary, real, or even complex variables. Right. I want to trade that representation for another representation which is quite nice. That's a representation in terms of loops, which I'm not allowed to call loops because they are cycles, but in physics they are called loops. And so the basic idea has already been explained several times. If you have a vertex I and a neighboring vertex j, so that there is an edge between the two, well, there are 2 situations. Either this edge here is part of the edge subset in the Fortuyn-Castelline representation. If that is so, then I'm going to define a transition system on the medial graph, which has also been defined several times, which does this. On the other hand, if this edge here is not part of the edge subset, then the transition system is going to do like this. So those things, those transition systems define a certain number of cycles or loops on the medial lattice. So the vertices of the medial lattice are the midpoints of the edges of the original lattice. And those transition systems, you can see they separate clusters from dual clusters. So they are kind of boundaries of the clusters. Now let n be any number of loops, n left, the number of loops touching left but never right, n right, the number of loops touching right but never left, and n both, the number of loops touching left and right. Well, then using the Euler relation, I arrive at this form of the partition function. So there's going to be an unimportant global factor, and then there's going to be these factors here for the various number of loops, and still these weights here.
Excuse me, I don't quite see what happens at the boundary. So are there actually loops, or do we have arcs somewhere ending at the boundary?
No, they are actually loops. So for example, so I should maybe have added that, I mean, suppose that, for example, this edge is here. There is something coming like this in the transition system. Well, then since it's constructed to turn around the clusters, it will link up like that on the boundary. Okay, so if this is part of a cluster which touches the left boundary, I mean if and only if, then the loop running around it will also touch left.
So so the loop touches the boundary if it actually goes through the boundary like that.
Yes.
It's not counted if it bounces off the boundary.
That is true. So
But then you have a little loop.
So you should imagine that on the medial lattice that there's a small, so this is a vertex of the medial lattice, and there's a small extra vertex of the medial lattice sitting out there on the boundary, and those are the boundaries, the boundary vertices for these cycles. Okay, so that gives me the boundary loop model, in which I now say that I have weight n for loops which never touch the boundary, n left and right and both for the others. And then the identification with the original coloring problem is as follows. Q is n squared, QL is n left, QR is n right, and QB is n both. I might even want to have, instead of a 4-parameter model, I might have an 8-parameter model, because I could give a different weight to loops which are homotopic to a point, or which are not homotopic to a point, because they exploit the periodic boundary condition. And those, evidently, they may also touch or not touch a given boundary. But I'm not going to consider that a lot. Okay. Now I'm going to present something quite different. So it's called a RSOS model. RSOS stands for restricted solid unsolid. It comes from physics. In mathematics, it might be called a graph homomorphism model. So the idea is that I want to define a partition function which is the sum over graph homomorphisms between my given graph and some target graph. Okay, so you should think about this in the following way. Instead of assigning colors to all the vertices, I assign values which live in some other graph. And there's a constraint, the homomorphism constraint. If two vertices are neighbors in the graph, then the values taken in the target graph are also going to be neighbors in that target graph. So that's why it's a graph homomorphism. On such models, in general, I can define, I can define interaction around a face. And so I'm going to consider only a particular case in which this original graph here is a connected plane quadrangulation. So it is derived from the original planar graph. It's not the medial graph, it's something else. It's actually the dual of the medial graph. And it's easy to see that that would be a connected plane quadrangulation. As far as the target graph goes, I shall need its adjacency matrix, which I'll call A. And I want to define some weights up in this partition function here. And those weights are going to be given in terms of an eigenvector of the adjacency matrix. Okay, so I've explained what my target graph is. The adjacency matrix is given. Now let psi be just any old eigenvector that you can find for that adjacency matrix, so that all entries are non-zero. So the entries are then indexed by the vertices of the target graph. And now I'm going to define a very particular RSOS model which has the following weights. So the weights depend on the values taken in this target graph. So so that the collection of those values are called sigma. And it's a product of weights with respect to individual vertices in my original graph and weights over the faces of my graph, which I remind is a plane quadrangulation. And they are going to take some very particular values in terms of the size. So every vertex comes with a weight psi sigma I. And for a face on my plane quadrangulation, if the 4 vertices on the face are sent to these values here on the target graph, then my face weight is going to be this. So there are inverses of the psi here. And then there are these delta functions which are trying to make the values be the same across diagonals. Either 1 or 3 are identical, or 2 and 4 are identical.
Jesper, so there's an edge of the original graph that's a diagonal of this quadrangular face, right? That's what the E is?
Exactly. So on this quadrangle here, either this diagonal is an edge of the original graph and this is an edge of the dual graph, or the other way around.
So what's your convention for the A sub E's and the B sub E's, and where the E sits relative to sigma 1 sigma 2?
Well, that will come in the theorem on the next slide. So for the moment, A and B's are just parameters. Okay. Okay. So down here's a drawing. So suppose that this is the original graph here in black, and here's the dual graph with open circles for vertices and dashed lines for its edges. Then here in red, you see the quadrangulation. So the quadrangulation, wait a minute, what's going on here? Wondering what the colors are. The colors seem to be slightly changed by the projection here. Anyway, so now here black is actually the quadrangulation. Okay, so you see that the quadrangulation always involves 2 vertices of the original lattice and 2 of the dual, and there's an edge of the original lattice which is one diagonal, and an edge of the dual lattice which is the other diagonal. And now there's the following theorem, which originally is due to a physicist, Kostov, which we have generalized and made the proof be more acceptable to graph theorists, I guess. So let G be a planar graph with a medial graph, and let gamma be this quadrangulation. I'm sorry, the star should have been outside, so it's the dual of the medial graph. And let the vertex and face weights be as above. Then there's a relation between the Potts model and the graph here. So the multivariate cut polynomial of the graph is related to the partition function of this RSOS model in this way here, where you see that the number of states, Q, is lambda squared, and lambda was the eigenvalue of this adjacency matrix. So that's a theorem. I could maybe use half an hour to prove it, but I'm not going to do that. So the only thing that you should keep in mind is that it's possible to represent a Potts model in general like an RSOS model of this type. Okay, now I'm going to try to sell you the following idea.
So this H was completely arbitrary here.
Yes. And in physics, it's almost invariably taken just to be a line graph. But everything holds true when it's an arbitrary graph. So 90% of the physics literature, it's a line graph.
A path. Graph theorists mean something else by a line graph.
Sorry.
The path.
A path, okay. I'm having my vocabulary corrected here.
And psi is any eigenvector of the adjacency matrix with no 0 coordinates.
Yes. Okay. I'm going to try to sell you the following idea. So in the beginning, I was talking about this loop model with two distinguished boundaries. That is going to be my big model, the biggest model. There's a smaller model, a more special model, in which I distinguish only one of the boundaries. So obviously that's a special case. So it's going to be a slightly smaller model in a sense, which will be made clear. Then there is the model in which I don't distinguish the boundaries, which is just the usual Potts model. That's going to be a slightly smaller model again. And then finally, there's going to be this RSOS model, which, if I go back here, requires Q to be something particular. That could not be defined for any value of Q. Q was required to take particular values. So there's a whole hierarchy of 4 different models. So the most general model has all these 4 parameters, and then there's less and less parameters. And in the end, even the number of states has to be something particular. And the main message today is that all those chromatic zeros, partition function zeros, they're going to be a result of a truncation of some more general model to a more special model. So you're going to find zeros when some parameters pass through values, so that a more general model can be reduced to a smaller model. And so I'm going to work with this hierarchy of models. So just think about the standard Potts model to RSOS model. So in the Potts model, Q can take any real value. And in the RSOS model, not all values of Q are possible, because Q is restricted to be lambda square, where lambda is the largest eigenvalue of some adjacency matrix. So I can't just find an adjacency matrix whose largest eigenvalue is, or whose eigenvalue is square root of pi, for example. That would not be possible. So I can't have the pi state Potts model represented in that way. So it can be shown that if this target graph is connected and simple, it's necessarily a Dynkin-Coxeter graph. And now if you want all weights to be positive, which seems reasonable for probabilists, then you should take, as this eigenvector, you should take the Perron-Frobenius eigenvector of the adjacency matrix. And that will then have lambda between 0 and 2. So in particular, if H is, which I should not call the line graph, what should I call it again? A path, AN, then lambda is going to be 2 cosine pi over n, where n is the number of vertices in the path. And of course, you immediately recognize that this lambda squared is nothing but the nth Beraha number. Okay, so lambda squared is 4 cosine pi over n. That's the nth Beraha number. And so that already tells me that something is programmed to be very particular when Q, which was lambda squared, when Q is equal to a Beraha number, what is so special is that the Potts model can be truncated to an RSOS model of the type that I have just described. And that is essentially going to explain why chromatic zeros like to condense at the Beraha numbers. And I'll come back to that later. So here is my complete hierarchy of models that I want to distinguish. So there's one called, okay, so this stands for 2 boundary temporally leap. So it just means a Potts model with 2 distinguished boundaries like defined over there. One boundary temporally leap is the same thing, but with only the left boundary distinguished. So the weight of a loop touching the right, but not the left, is going to be the same as a bulk loop, have the same weight as a bulk loop. And something touching both is, of course, touching left, so NB is N left. So that's a special choice of parameters which will make this model here truncate to this model, and that will give partition function zeros. And then here's the usual Potts model, which I'll call 0 boundary temporally leap. Same thing as above, but with L left equals to N. So when N left goes through n, then there are going to be partition function zeros again. And finally, all these Bérard zeros, they are going to deal with this last truncation here when n, the weight of a loop, which is square root of q again, takes the value lambda, and that is only possible for particular discrete values, for example, of this type here, if an is this path. So, let me move on to the transfer matrix formalism. So, Professor Biggs has already shown us how it's possible to use a transfer matrix in the original coloring picture to construct the whole partition function, and how the structure of that transfer matrix is going to be responsible for these limiting curves of accumulation points of zeros. So I'm not going to work within the space of colorings. I'm going to work within the space of these clusters or loops. So instead of having transfer matrices whose size will vary when I vary the number of colors, I'm going to have transfer matrices of a constant size whose eigenvalues come with some multiplicities, exactly the same multiplicities as Biggs worked out, but we're going to think of this in another way. Okay, so let me describe this for the ordinary Potts model. So suppose I take a regular lattice of a fixed width embedded in an annulus, like over here, and let me try to build up the loop model by action of elementary generators so that I sort of construct the lattice going upwards. So then the elementary generators are the following. So suppose that I'm going to add, say, an edge of my graph, and there are two boundaries coming in here. Those are those of the loop models. Then if I choose to include this in my special edge subset, then these two guys here are going to bounce off. So there's an identity operator acting on them, whereas if this edge here was not present in the edge subset in the Fortuyn-Castelline representation, well, then I have to do this. So there's some operator acting on the two strands here, which is called a Temperley-Lieb operator, and which looks like this. So this is actually, suppose this is the kth strand and this is the k+1 strand. Then this thing here, this object, contracting them like that is called EK, and that's a generator of some algebra, and it's called a Temperley-Lieb generator. And on the boundary, nothing happens. I mean, if you go out to the boundary, what happens is just what I have drawn over here. You just bounce off the boundary. So on the boundary, you can only do things like that. So on a small portion of the square lattice, this will look something like this. So these loops here are doing things like that. And one crucial thing that you have to notice is that if I'm constructing my lattice going in that direction, there'll be a certain number of segments going between top and bottom. So you see here is one, and here's another one. And they're also going to be closed loops or cycles, if you wish. And one crucial thing is that the number of strands going from top to bottom can only be decreased by the action of the transfer matrix, because it might happen that two things which extend down to the bottom are being linked up in this way, and so they will be annihilated. But there can never be any more of those guys created as I go along. So the transfer matrix is going to have an interesting structure that I'm going to use presently.
I'm sorry, at the level of loops, isn't the number of strands is just n, the number of vertices, the width, right?
Right. Yes.
It's at
Exactly.
the level of Fortuyn-Castelline clusters where what you just said.
Well, you see, if the system is of width 2 vertices in the original Fortuyn-Castelline representation, then in the loop representation it's going to be of width 4, because I need these guys here to go around the clusters on both sides.
I'm sorry, so let me rephrase. So in the loop representation, the point is that when you annihilate a loop, you'll create the same number of strands. It's not that you have fewer strands. It's the top strands are not connected to the bottom.
Exactly.
So if you ask how
Exactly. So if I ask how many guys are connected all the way down to the bottom in some way, then that number can diminish. The number of strands seen across the system is a constant. But the number of strands going down to the bottom can decrease but never increase. And so eventually when I glue the system together with these periodic boundary conditions here, that is going to mean something about the number of non-contractible cycles that I can have. Okay. So my transfer matrix now has to act on all pairings of 2L points here respecting planarity. And just to show you what that would look like if I also distinguish the left boundary, here's a complete list of the states on 4 strands where the left boundary has been distinguished. Okay, so you see there are some states where there's a maximum number of strands connecting top and bottom. And since the leftmost guy always touches the left boundary, it's going to have a special mark on it. It's a small circle. So the small circle means that this guy at some point has touched the left boundary. And then there are going to be also states where there's a smaller number of strands extending throughout the system from top to bottom, and the remaining strands are connected in some other way. And then there are these marks which can be in all kinds of positions. So every strand which can see the left boundary has the possibility of carrying this circular mark here. So this one in here, that one is protected from seeing the left boundary by this. So it cannot have the mark. So here's the list of states in which I'm supposed to act. And so if I keep acting on the top here with my transfer matrix in terms of these generators and the identity, then I'm going to evolve these states here. So that's going to define some matrix. And eventually, to construct the partition function, I just have to apply the transfer matrix a number of steps which is equal to the height of the lattice. And then eventually I have to identify top and bottom. And that is not an innocent operation, because the partition function is not going to be the trace of the transfer matrix. It's going to be a trace weighted by the number of loops which are created when I identify top and bottom. And it's because that weighting is non-trivial that I'm going to have the partition function not just as a sum over eigenvalues with each eigenvalue raised to some power, but there's also going to be a number multiplying it, which is an amplitude. And those were worked out by Biggs in the
If you identify
preceding
top
talk.
and bottom, then the distinction with this little circle becomes less clear, because then, for instance, in the bottom, the inner circle is part of a bigger thing which actually touches.
Right. Well, everything is well defined, actually. So, for example, suppose.
Here in the bottom.
So suppose, for example, this guy here, I identify top and bottom.
Yeah.
Well, this half loop here has touched the left boundary, and this one has never touched the left boundary. So what does it mean? Well, it means that somehow I have a situation like this, and I identify this point with this point, and this point with this point. And so the total loop here has touched the left boundary. So these circles here, they're like measles, they are contagious. So if there's something which is not ill yet, it will be it when it touches another guy which has the disease. Right. There's an algebraic structure behind all of this, which is called the Temple-Lieb algebra. So the idea is that if I start stacking these generators here, I should generate some relations. So let's just look at the top relation here. So if I have some EI and another EI, well, then that's going to be this. It's going to be the same thing, but with an additional loop. So the loop has to come in with some weight, n. Okay, and there's also this nice relation here. If I work on 3 different strands, if I take first EI, then EI plus 1, and then again EI, then I can stretch out this strand here, and it's going to be the same thing as just EI. So you can graphically prove these relations, so that defines some algebra, which is called the Temple-Leap algebra on a certain number of strands. And for the case that I've described here, where the left boundary is distinguished, there's a similar algebra, which is called the one-boundary Temple-Leap algebra, or sometimes the blob algebra. And it has an additional generator BL, and the BL acts whenever I go out here and touch the boundary. So that's the generator which is acting the circle. Okay. So there's a first relation here saying that if I have some strand and I act with it on BL, and if I do it again, well, it just means that it has seen the left boundary twice, but I don't care. All that matters is that it has seen the left boundary at least once. So it's the same thing as this. Then there's a small relation here saying that if I do E1, then I see the boundary and I do E1 again. That's the same thing as E1 times not N, but NL, because this loop here has seen the left boundary. So there's an algebraic structure behind that, and there's another algebraic structure in the 2-boundary case, which I don't want to write. So suppose now that I want to write my transfer matrix, I want to sit at the critical point for the square lattice model. This is just an example. You could do any lattice that you want. Well, then the transfer matrix is going to look something like this. At each stage, when you add an edge, either the edge is going to be in the edge subset or it's not going to be there. That's what I just explained here. So you're going to get a product like that, and then there's this guy here acting on the boundary. So now this transfer matrix has got an interesting structure, because let me go back here. So those are the states on which it is acting. Suppose now I cut a state horizontally through the lines, the strands which connect top and bottom. Then it's going to fall apart into 2 separate states, which I shall call reduced states. And now you see what happens is that, for one thing, the transfer matrix can only decrease the number of lines going through. Okay. No, that's not what I wanted to say first. What I wanted to say is that if I have a certain pairing of the points down here, then if the transfer matrix acts up here, it can never change the pairings down here. Okay? So for a fixed number of pairings here, the transfer matrix is never going to get you outside that space, so it's block diagonal with respect to what goes here, goes on here. It's also block diagonal with respect to the anchoring points of strands which run through the system. Okay, so it already has a huge structure, and the second structure is that the number of strands going through can only be diminished by the transfer matrix. At best, I can leave them unchanged, and at worst, I can use this Temple-Leap generator to link them up, and then there'll be a fewer number of strands going between top and bottom. Okay, so T is block diagonal with respect to the lower half state, or the reduced state, which means that all its eigenvalue can be gotten by acting just on the upper half states. And it's also lower block triangular with respect to the number of through lines, and hence, for the purpose of finding the eigenvalues, I might as well just fix the number of through lines, because if I have a block triangular matrix, then the blocks on the diagonals are going to give me all its eigenvalues, evidently. So that will define what I call a sector TL of my transfer matrix, in which the number of through lines has been fixed to L. And then finally, then there was this blob, the circle acting on the boundary. Well, as I said, it's contagious. Once you have marked a through line, then now, since you have fixed the number of through lines to be a constant, that marking can never disappear again So it's block triangular with respect to the marking or the blobbing of the leftmost through line. And so it means that I might as well find my eigenvalues in small blocks which have a fixed blobbing status of the leftmost line. That is to say, either I force the leftmost line always to carry the circular mark, or I force it never to carry it, and that I'm going to call the blobbed sector and the unblobbed sector. Okay, so every eigenvalue of the complete transfer matrix, an enormous object, is going to be an eigenvalue of these matrices here, which are much, much smaller.
Yes. I'm worried that people may not have time for lunch.
I thought I had 1 hour.
No.
I think so. We started at 11:30, right?
Sorry, Jesper.
Okay, no problem. Okay, so that leads me naturally to my next thing. So the eigenvalue amplitude. Okay, so identifying top and bottom, that is going to mean that my eigenvalues come with some amplitude. Okay, so the partition function for an annulus of width n and length m, I shall take the width to be even, is not simply the trace of the transfer matrix trace of t to the n I should have written. The eigenvalues come with amplitudes, and those amplitudes I can work out. So for example, in the case with one boundary, there are going to be amplitudes which I shall call du for the unblobbed sectors with 2j through lines, and dB for the blobbed sectors with 2j through lines. And the case here, are going to be genuinely traces of the transfer matrix, so they are just going to be lambda to the power m summed over the dimensions of these small transfer matrices. So now I'm not going to derive what these things here are, but I'm going to say at least that there's a combinatorial method for determining them which is completely rigorous, which works just in terms of generating functions. And the idea is that you take this linear system here, and instead of solving it for z, first you solve for k. If you do that, so you try to express the k's in terms of the z's, then it's a counting problem. You just have to count some positive integers. So you can deal with it using generating function techniques. And once you have got that counting, you invert z, you invert it and get z in terms of k. And the result is the following. So if I have the two boundary k's, then my eigenvalue amplitudes, well, there are 4 of them corresponding to whether the leftmost and the rightmost line are forced or not forced to touch the left or the right boundary. So unblobbed, 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 blobbed, blobbed, unblobbed, blobbed, blobbed, okay. And they are given like linear combinations of 3 Chebyshev polynomials of the second kind. In the one boundary case, it's going to be linear combinations of Chebyshev polynomials, only 2 of them. And then this result here we already saw in the talk of Schrock, and again in the talk of Chang. In the case where you just have the ordinary Pottsmall, it's just one Chebyshev polynomial. Okay, so maybe I should have given it in the reverse order, going from the most particular to the most general. Okay. And finally, the RSOS case, my smallest model, well, that was just given in terms of some honest to goodness variables which had nothing non-local in them over which you could just trace. And so all the amplitudes are trivial and equal to 1 in that case. So
that's the case not where the target graph H is arbitrary, but where it's a Coxeter Dinkin diagram. So you get a
right.
numbers.
Yes. Okay. So suppose now that one of these amplitudes multiplies the dominant eigenvalue in my transfer matrix. Well, then the zeros of these polynomials here are going to be very important, because by the Biraka and Weiss theorem, they're going to tell me where the isolated limiting points are. Okay, so that's my one half of my main message. Okay. And so the fact that these guys here are going to vanish, that is going to single out the Biraka numbers. But now, what does it mean that these guys here vanish, or these guys vanish? Well, that's clearly going to be more complicated things. So let me come to that. Here's a very short section on conformal properties of these models, where I'm not going to enter at all the proofs. I'm just going to state the results. So if you were here last week, you will have learned that unitary minimal models in conformal field theory are described by some critical exponent called the central charge, which can be parameterized in this way, and p is required to be an integer larger or equal to 2. And there are scaling dimensions, critical exponents, if you wish, which are given like this and parameterized by r and s, which are supposed to be in some range called the Katz table. Okay, and just summarizing, the ordinary Potts model has this central charge. If I put the weight of a loop, so square root of q equals to 2 cosine gamma, and gamma is pi over p plus 1, p an integer, and the leading exponent, so the most relevant exponent describing the sector TL of the transfer matrix, is HL equal to H1 comma 1 plus L, given by this formula here. Okay, so I know exactly in the limit of a large lattice, I know exactly how the probabilities of having a given number of through lines, how that decays exponentially with the length of my strip. That I know exactly, and the result is given by these exponents here. Okay, and now here are, P was linked to n, so it's just a way of parameterizing n. Okay, so there are many parameters in here. I'm kind of sorry. So the Q state Potts model corresponds to a loop model with weight n, and that n I like to write as 2 cosine pi over p plus 1. Okay, so p plus 1 is the Baraha number, if you wish.
Q is the Baraha number.
Corresponding to the p plus 1 Baraha number, right. Okay, so here's just a summary of the same things that we have done for the 1 boundary and 2 boundary case. And so now here, there is something going on that I simply don't have the time to explain. So it turns out that NL, so the weight for a loop touching the left boundary, should be parameterized in this way. So there's some R here, RL, okay? If you do that, just imagine that you parameterize it in that way, then the leading exponent of the sector with L through lines and the leftmost line forced to touch the boundary is HR, R plus L, I'm sorry, R should have been R left, of course. And if you force it not to touch the boundary, it's HR, R minus L. Okay, so just in 10 seconds, where does this come from? Well, it comes from the theory of integrable systems, and it comes from representation theory of an underlying 6-vertex model. Okay, but never mind. It comes from somewhere, and it's just true. Okay. In the 2-boundary temporally leap case, I should parameterize similarly the weight for touching the right boundary. And now the thing which looks pretty awful is that the weight for touching both boundaries should be parameterized in this fantastic way here. So there's a very good reason for that. And if I do that, then the leading exponents for all these 4 sectors are given by expressions like that, when the number of through lines is non-zero, and if it's 0, it's given just by this.
But the central charge is the same as in the no boundary case?
And the central charge is the same. Okay, so all of this is just boundary effects. Okay, the central charge is only fixed by the weight for a loop not touching the boundary, simply for the simple reason that if the system is enormous, then it's going to be completely dominated by such loops. The loops touching the boundary are going to be rare. So they just play on the level of the critical exponents. They don't play on the central charge. Okay. So of course it seems completely outrageous that this expression should be so simple here, and in particular it does not depend on RL and RR. except that NB is linked to RL and RR through this parameterization. So this parameterization, that's kind of a miracle, and unfortunately I don't have the time to explain you where that miracle comes from. So we know the conformal properties. So now let's go to partition function zeros. With all that being swept under the rug, let me then review the Biraka and Weiss theorem for the 10th time in this conference. So partition function zeros will accumulate as the height of my strip goes to infinity to either isolated points if the amplitude of the dominant eigenvalue vanishes, or to curves if two dominant eigenvalues are equimodular. How can I get things like that in this setup? Well, the D's I have computed for you in these cases with boundaries. So you know when they vanish. How do I get, okay, so I pretend that I know something about the real accumulation points. And so in the real Q plane, I know something about where the accumulation points are from conformal field theory. And the key point here is that if I fix a given sector of my transfer matrix, okay, and then if the maximum eigenvalue, if I call that lambda L, then if I define FL as the corresponding free energy, so it's 1 over n log lambda L, it turns out that that has a size dependence which is as follows: FL of n minus F0 of n. According to conformal field theory, it's 2 pi h L over n squared plus higher order correction terms. Okay? So what does this mean? It means that in the limit of large n of large width, conformal field theory tells me that if I know these critical exponents here, I know which dominant eigenvalues in each of these sectors here are the largest, because I simply have to look for the least possible value of h. Okay? So in any normal probabilistic case, of course, the thing which is going to be the least corresponds to L line going through. I mean, that is not mysterious at all. It's just, imagine you have this very, very long strip and think of these lines here in a probabilistic sense. The most probable thing surely is going to be that there is no lines going throughout the system, because the strip is so high and so small. Okay, but the case that you're interested in, this chromatic zero business, well, that's a region of phase space where the model is antiferromagnetic, and it's not probabilistic at all. So what happens is that some of these exponents here are negative. So it's more probable, for example, in some regions of phase space to have two lines going throughout a very long, very thin strip than having no lines. So probable, quote unquote, okay? And so to find the dominant sector, I should just find the least exponent, that is to say the most negative exponent. Okay? And I promised Alan not to mention quantum group symmetry, so I won't. Okay, so here is, I guess, no, it's not quite my last slide. Almost, my second to last slide. Okay. Now I have to tell you a little bit about what happens, for example, on a few regular lattices. And then let's see how those things are going to be generalized in the case of an arbitrary planar lattice. Okay, so if you take the square lattice, then what is known about the phase diagram in the QV plane? Well, it's known that there's a line of critical points where V is equal to plus minus square root of Q. And it's known also that there's another thing here with v equals -2 plus minus square root of 4 minus q. So those are curves on which the system is critical. This is the ferromagnetic-paramagnetic phase transition. This thing here is just the analytic continuation of that into the antiferromagnetic regime. And it turns out, if you work out the conformal field theory, that along this line here, a deviation in this variable v is irrelevant. So whenever you sit somewhere here, then if you look on your system on larger and larger length scales, you're going to renormalize down to this region here. So this whole region here is controlled by this line, okay? And now the crucial thing is that along this line, some of these exponents are negative. So you can make some of these sectors TL be the dominant guys. And when dominance switches from, say, L to L plus 2, then you are going to satisfy the criterion of the Berat-Cahen-Weiss theorem. And then you are going to have, in the complex Q plane, you are going to have these branches which go down and cut the real Q axis in the Berat numbers. Because that, if you just work it out, you'll find out that this change of dominance happens exactly at the Berat numbers. Right. Now the chromatic line. The chromatic line is v equals -1. And it intersects this phase here between q equals 0 and q equals 3. So within that region of phase space, this line here, for which I have a conformal field theory, is going to tell me what the chromatic polynomial is going to look like. That's for the square lattice. There are similar results for the triangular lattice, in which it just turns out that there's a similar phase here, but the chromatic line cuts it not at 3, but at 3.8 or something like that. So you'll see a little bit more of all these Berat numbers, okay? So I believe I have explained all of this up here. Okay, and now let's look at the case with a boundary. Let me parameterize this gamma, which disappeared, but 2 cosine gamma. So square root of q was 2 cosine gamma. Let me parameterize gamma in this fun way. Then the exponents are going to look like this, and the amplitudes are going to look like this. And I see from those expressions that there are going to be level crossings involving the dominant sector. So that's to say HL equals HL plus 2 whenever R, remember R was the thing that parameterized the other weight, right? So there was N, which was 2 cosine gamma, and there was N left, which was sinus RL pi gamma over sinus RL plus 1. There's no pi gamma. When this R takes these particular values here. Okay? And the dominant eigenvalue vanishes when R is equal to this. Okay. We come to my main method. I hope I haven't lost you too much. In the usual Potts model case, a loop touching left has the same weight as an ordinary loop. So you just look at these two parameterizations, and it's obvious that they are identical if RL is equal to 1. So it's R equals to 1, okay? So what do I see here? Well, L was the number of through lines, so that's an integer. Now R is 1. And T, that's the Tth Berat number, okay? So I have level crossings or vanishing of dominant amplitudes exactly when T is equal to an integer. So that is why Berat numbers are important in that case. However, had I chosen to give a different weight to loops touching the left boundary, then this RL would not be equal to 1 anymore. And then you see that there is nothing at all particular about the Berat numbers. T does not necessarily come out as an integer at all. Okay, so there was one striking example of that in Chang's talk, if you had the time to see it, what he had done was to take a square lattice with self-dual boundary conditions. So he had this long strip, and on the left-hand side, he had added one more side to everything on the boundary. What does that mean? It means that this is going to take a given color, and all of these here can then only take q minus 1 colors. Okay? So for all of these guys here, I have NL, QL equals q minus 1. And if I think about what that does, well, that will just exactly swap things around so that Chang had level crossings where normally you would have dominant amplitudes vanishing, and the other way around. And now I claim that if you take a more general choice of this QL here, you can just move around the zeros as you want. Nothing particular about the Baraha numbers. Here is an example for the 3-state Potts model. Okay, so here's my prediction. You take a lattice for which q equals 3 belongs to this face here. So take the triangular lattice just to be sure. Okay, fix q to 3 and start varying QL, the number of surface colors. You start varying that continuously. Well, now as a function of this parameter r here, r in this parameterization here I have simply drawn what the most relevant exponent is, the most relevant h, and I recall that you should look for the one which is the least possible. So there is the black one is h0, h2, h4. I believe this should be h6. I have written h8, sorry. Okay. And so you see, whenever there's two dominant guys crossing here, I'm going to have in the complex QL plane, I'm going to have this branch cutting through the real axis. And whenever there's a cross here, it means that the dominant amplitude is vanishing, and so I'm going to have an isolated point. Okay? So the number of boundary colors which will do that for me corresponds to 0 colors on the boundary, 1 color, 3 half colors, 2 colors, 3 colors, and infinity colors. So that's my prediction. I went 7 minutes over time, but I arrived at this thing here that fix q varies the number of colors on the boundary, and you're going to see multiple phase transitions, and the loci where they are going to be, that is exactly predicted by this thing here. Thank you for your attention. Surely I did scare you somehow.
Less so than last week.
The Baraha conjecture is that the Baraha numbers are accumulation points for plane triangulation.
Right. Mm-hmm.
And is it that those are the only accumulation points, or that they are, just that they are accumulation?
Well, apart from points such as, say, 3 here, well, that happens to be a Baraha number, but that's kind of a coincidence, or 0, where you actually leave this hatched region here. They are the only ones. But there might be additional accumulation points on the real axis where you just go outside this region here, which is described by conformal field theory, and until something which is described by a free energy which has just a completely different analytic expression.
I think I was asking what is the conjecture? Could you remind me of the conjecture?
So Baraha's conjecture, well, I mean, I think that his main conjecture was that chromatic zeros were going to accumulate at these Baraha numbers for any plane triangulation.
Yeah, I mean, you can imagine
So in
variance depending on what classes of graphs.
But is the conjecture
So in that sense,
they are the only accumulation
I
points?
think there might be two different versions of the
Well, I mean, in that, if that were the case, that would not be quite true, because on the triangular lattice, something would accumulate at this particular value here, where this chromatic line goes outside this phase described by conformal field theory, and that guy is not a Baraha number. So, except for a limited number of cases like that, where you simply switch from one theory to another theory within, conformal field theory or something, I think that the Baraha numbers are the only ones, provided, of course, that you don't start fooling around with a different number of colors on the boundary, like I just did here in my talk.
I mean, I guess it depends what class of graphs you're considering, because if Karsten's conjecture is true, that chromatic roots of plane triangulations are dense between 32 27ths and 4, then every number is an accumulation point of some sequence of graphs.
Right.
But maybe the point is for more structured families of graphs.
But like plane triangulation.
And so, for example, in Gordon Royal's talk, he had this real zero which tended to 4, right? For things which were essentially variations of the triangular lattice. And so the important thing is that 0 is going to belong to a phase which is outside of what has been described here by conformal field theory. So so generically it sort of belonged to this region between 3.82 and 4. Okay, so in that region there is absolutely no telling what can happen. That I can't really say anything about that.
I don't know if Karsten is still here.
No.
So I don't know what the version of his conjecture. I mean, for plane triangulations, we know that there are some gaps between 32 27ths and 4, but
Yeah, there's
maybe
a gap all the way up to 2.54.
right. But maybe after 2.54, it's dense up to 4. I don't know.
Maybe, as you said, that will be opposite. That sounds a lot different to the Baraha conjecture for plane triangulation, if it is of the form that the only accumulation points are the Baraha numbers. So there seem to be two extremes.
Well, there were trivial examples. Aren't there? I mean, aren't there trivial examples of accumulation points that are not that you build? I mean, if the graph doesn't have enough, if it's not reconnected or something.
Connected.
Otherwise, you could just put things inside other things.
But then,
If you make the strip wider and wider, will they revert to Baraha numbers then?
No.
So no matter how wide you make the strip, as long as you choose this boundary condition, basically,
Right.
it'll still change the locations of the zero.
So here, of course, what I have plotted here are the critical exponents. So those are giving you the level crossings in the limit of an infinitely wide system. Well, now the thing that Alan has forbidden me to say is that there are quantum group symmetries in this problem. So actually the quantum group symmetries will make that even though this has been derived for infinite width, it will hold for any width. These level crossings are going to happen exactly in the same places even for a strip of width 2, if you want. Okay, so even in finite size, so for a finite width, infinite height strip, you're going to see accumulation points sitting exactly at the values predicted here, but to explain that fully I would have to identify the underlying quantum group symmetry and tell you why there is no size dependence, but there is none. Sorry. I ended up saying it anyway.
Quantum groups. It's certainly nice.
Trying to stay out of it.
can we thank Jesper again?